Good morning, students. So, in my lecture series, data structure using C++, so I am going to cover in this class the basic concept of algorithms. So, what is algorithm? How we apply algorithms in C++ programming? So, first we know what is algorithms. For that, we go this some slides. So first we see what is algorithm. So algorithm is a step-by-step procedure which defines a set of instructions to be executed in certain order to get the desired output. So algorithms are generally created independent of underlying languages. That is, an algorithm can be implemented in more than one programming language. So from data structure point of view, some important characteristics or some important categories of algorithms are found which are given below. For example, search. So algorithms to search an item in a data structure. So sort. So algorithm to sort items in certain order. It may be ascending or descending. So insert. Algorithm to insert items in a data structure. So next, update. Algorithms to update an existing item in a data structure. So delete. So algorithms to delete an existing item from data structure. These are the categories of algorithms, how we do some operations in programming. Next, if we see the characteristics of an algorithm, so not all procedures can be called an algorithm. So all procedures may not be an algorithm. So to be an algorithm, it must follow some characteristics. An algorithm should have below mentioned characteristics. So number one, unambiguous. So algorithms should be clear and unambiguous. Each of its steps, phrases, and their input output should be clear and must lead to only one meaning. Number two, input. An algorithm should have 0 or more well-defined inputs. So without inputs, we cannot proceed for an algorithm. So next, output. An algorithm should have 1 or more well-defined outputs and should match the desired outputs. So finiteness. So algorithm must terminate after a finite number of steps. So feasibility. So algorithms should be feasible with the available resources. Next, independent. An algorithm should have step-by-step directions which should be independent of any programming code or language. So if we see the problem, we design an algorithm to get solution of a given problem. A problem can be solved in more than one ways. So problem, solution 1, solution 2, solution 3, solution 2 means we can design more than one algorithms for a same problem. So algorithm analysis, if we see efficiency of an algorithm can be analyzed at two different stages, before implementations and after implementations. So one is a prior analysis. This is the theoretical analysis of an algorithm. Efficiency of an algorithm is measured by assuming that all other factors, for example, processor speed, are constant and have no effect on the implementations. Number two, a posterior analysis. This is the empirical analysis of an algorithm. The selected algorithm is implemented using programming language. So this is then executed on target computer machines. In this analysis, actual statistics like running time, space required are collected. So we shall learn here a priori algorithm analysis. So algorithm analysis deals with the execution or running time of various operations involved. So running time of an operations can be defined as number of computer instruction executed per operations per unit times. So algorithms complexity. If you see the complexity of an algorithm, so suppose X is an algorithm and N is the size of input data that the time and space used by algorithm X are two main factors which decide the efficiency of X. So time factor, the time is measured by counting the number of key operations such as comparisons in sorting algorithm. Similarly, space factor, the space is measured by counting the maximum memory space required by an algorithm. So the complexity of an algorithm Fn gives the running time and storage space required by the algorithm in terms of n as the size of input data. So now space complexity. The space complexity of an algorithm represents the amount of memory space required by the algorithm in its life cycle. So space required by an algorithm is fixed part plus variable part. So a fixed part, that is a space required to store certain data and variables that are independent of the size of problem. For example, simple variables, constant, use program size, etc. Number 2, a variable part is a space required by variables whose size depends on the size of the problem. For example, dynamic memory allocations, recursion, stack space, etc. So space complexity SP of any algorithm P is SP equal to C plus SPI, where C is the fixed part and SI is the variable part of the algorithm which depends on instruction characteristics I. So for example, algorithms sum AB, here we have three variables A, B and C and one constant. So step 1 start, step 2 C equal to A plus B plus 10, step 3 stop. So here hence SP equal to 1 plus 3. Now space depends on data types of given variables in constant time and it will be annotated accordingly. So the time complexity, if we see the time complexity of an algorithm represents the amount of time required by an algorithm to run to completion. The time requirement can be defined as a numerical function of Tn, where Tn can be measured as number of steps provided each steps consume constant time. For example, addition of two n-bit integer takes place in steps. So total computation of time is Tn equal to C star n, where C is the time taken for addition of 2 bits. Here we observe that Tn grows linearly as input size increases. So asymptotic analysis. So asymptotic analysis of an algorithm refers to defining the mathematical bound or framing of its runtime performance. So using asymptotic analysis, we can very well conclude the best case, average case and worst case scenario of an algorithm. So asymptotic analysis are input bound. If there is no input to the algorithm, it is concluded to work in a constant time. Other than the inputs, all other factors are considered as constant. So asymptotic analysis refers to computing the running time of any operations in mathematical units of computation. For example, running time of one operation is computed as Fn, and maybe for other operations it is computed as Zn squared, which means first operation running time will increase linearly, which increases in n, and running time of second operation will increases exponentially when n increases. Similarly, the running time of both operations will be nearly same as n significantly small. So linear versus exponential. So this is linear and this is exponential series. So usually the time required by an algorithm falls under three types. Base case, that is minimum time required for program execution, run fastest among all inputs. Average case, average time required for program execution gives the necessary information about algorithm's behavior on random input. Worst case, that is maximum time required for an program execution, run slowest among all inputs. So asymptotic notations, we have following are commonly used asymptotic notations used in calculating running time complexity of an algorithm. So big O notations, so delta notations and theta notations. So big O notations, O, that is order of n is the normal way to express the upper bound of an algorithm's running time. It means it measures the worst case time complexity or longest amount of time an algorithm can possibly take to complete. Next, omega notations, that is the omega notation. Omega of n is the formal way to express lower bound of an algorithm running time. This measures the base case time complexity or best amount of time an algorithm can possibly take to complete. Now theta notations, theta n is the formal way to express both lower bound and upper bound of an algorithm's running time. So to analyze an algorithm, first we start to count the number of significant operations in a particular solution to assess its efficiency. Then we will express the efficiency of algorithm using growth functions. Then each operations in an algorithm has a cost. Each operations take a certain of time. Count equal to count plus take a certain amount of time, but it is constant. A sequence of operations, so count equal to count plus 1 or sum equal to sum plus count. So cost is equal to C1 for this count, and for sum C2, then total cost C1 plus C2. So how we see if what is happening? Simple if statement. If n less than 0, so absolute value equal to minus n. If else absolute value equal to plus n. So their cost C1 1 times C2 1 times C3 1 times, so total cost equal to less than equal to C1 plus maximum of C2 and C3. So loop, for case of loop, for I equal to 1 sum equal to 0 while I less than equal to n, I equal to I plus 1 sum equal to sum plus I. For this loop we have cost and time, so this is C1 1 time, C2 1 time, while C3 equal to n plus 1, C4 equal to n, C5 equal to n. So total cost C1 plus C2, n plus 1 into C3, n into C4, and n into C5. So total time required for algorithm is proportional to n. So nested loop, then we have n squared. Here equal to this, some this, then again while this, for this we have this loop. So space n squared. Space complexity is a function ABC. So this is the word, so space complexity. So loop, so function sum. This is the algorithms and the space n is n. Yes, so s sum less than plus 3. Recursions. The function means the function call itself. So here this general rules for estimations. Loops, the running time of the mass with time is the number of iterations. The nested loop, running time of nested loop containing a statement in the innermost loop is the running time constant multiplied by the product of size of loops. Consecutive statement, just added the running times of those consecutive statements. If else, never more than running time of the tested plus and larger running times of S1 and S2. So algorithm growth rates, we measure an algorithm's time requirement as a function of problem size. So problem size depends on applications, number of elements in list. For sorting algorithms, the number of these that are having. So algorithms proportional time requirement is known as growth rate. So we can compare the efficiency of two algorithms by comparing the growth rate. So growth rate, if we see, this is the algorithm B required 5 into n second, and this is the algorithm I required n squared by 5 seconds. So time requirement as a function of size n. This is different growth rate. So common growth rate is C constant, log n, logarithm, log square n, log squared, n linear, n log n, n square quadratic, n cubic. over an exponential. This is the common growth rates of an algorithms. So running times for small inputs. So this is linear, this is log n, this is quadratic, and this is cubic. And running a modern, so this is linear, this is log n, this is quadratic, and this is cubic. So space complexity. If we see the instance here, this is how we can find shape complexity. So thank you. Good day. This slide I ended my class. Okay, thank you.